All right, well, welcome everybody to the Arctic T-Slip webinar series. I'm really glad you were all able to be here. We're all experimenting a little bit with this summer model, and I know summers are very busy, but I'm glad that you could all be here. Just to give you a little bit of background, so if you're new to this group, Arctic T-Slip stands for Arctic Tsunamigenic Slope Instabilities Partnership, and we're a team of folks who are working on an NSF funded planning grant, which is part of a much broader extended Arctic sea slip network that is focused on several main goals, but I'll share those in a moment. And our team includes all of you. So one of our goals is working on future proposals. And so we hope that you'll consider becoming more engaged in our network and team and work as we progress here. So just to kind of situate this work, overall, the Arctic T-Slip mission includes fostering connections among a diverse group of people that are all interested in landslide and landslide-generated tsunami hazards, generating a shared understanding of these hazards in cryosphere-affected regions, and facilitating collaboration to identify and frame research needs so that we can together build a foundation for future projects and actionable solutions. And our big picture goal here is a NSF planning project goal. So by the end of 2026, we'd like to submit a nested group of research proposals to the NSF Office of Polar Programs on landslides and landslide-generated tsunami hazards. So through this work, we're identifying research needs, coordinating research ideas and resources, and trying to find project leads to lead teams and future proposals. And for everybody on the call here, just want to call attention to the Save the Date, where we'll be having a workshop really focused on proposal writing February 24th to the 25th in Anchorage, Alaska. So please get in touch if you're interested in leading proposals or finding other ways to get more involved in this work. And before we turn it over to our presenter for today, I just want to give everybody a heads up about some future webinars that have been scheduled in the coming months. So our next webinar is going to be a panel discussion with three different emergency managers from across Alaska. And this is going to be a really interesting discussion. So I hope that many of you can make it for that. The next presentation on July 18th will be focused on local monitoring and warning systems, where we'll be hearing from some of the folks who've been working on the QT project in Sitka, Alaska. In July, on the 25th, we'll hear more about some landslide social science, specifically communication science, from Sarah McBride, who works with USGS. And then on Friday, August 8th, we'll be having a presentation from Carl Bonivi Harbitz in Norway on landslide-generated tsunami work that's happening in Norway. And so if anybody is interested in presenting in a future webinar or interested in a specific topic, please let us know, and we'll see what we can do to schedule that in the future. And I'll put these links in the chat, but if you're not already connected with Arctic T-Slip, please join our email list. That's where you can easily learn about future webinars and activities that are happening as part of the project. You can also watch for us on YouTube, Facebook, and LinkedIn. And just finally, I want to give everybody a heads up that we're recording today's presentation, and we'll share this on YouTube afterward. But we will not be recording the discussion and question and answer session at the end of the webinar. And we will be taking notes during the presentation and during the Q&A to just contribute to our proposal and brainstorming as the project moves forward. So with that, let me stop this, and I am going to turn it over to Dr. Yang Wei, who is going to present on tsunami forecasting and hazard assessment. And so please take it away, Yang.
Right, thank you. Let me share my screen first. So do you see it?
Yep, it looks great.
Okay, great. So yeah, good morning. Uh, my name is Yang Wei. So truly grateful for inviting me to share our research on tsunami modeling and to connect with the TISLIP community. So in today's presentation, I will provide an overview of the tsunami research that have been involved over the past few years, focusing on tsunami model application in forecasting and hazard assessment, along with a look at some of the ongoing efforts that may align with the goals of TISLIP. So about myself, I'm currently a senior research scientist and lead PI of the Tsunami Group at the Cooperative Institute for Climate, Ocean, and Ecosystem Studies, CECOS, at the University of Washington, Seattle. CECOS is a consortium for fostering research collaboration between NOAA and the UW and U of Alaska Fairbanks, and also Oregon State University. Seacoast Tsunami is a critical and component of the NOAA Center for Tsunami Research, which is a unit of NOAA's Pacific Marine Environment Lab to support NOAA's mission towards tsunami warning and forecasting. We work very closely with both tsunami warning centers to develop NOAA's tsunami forecast system. So I got my PhD degree in ocean engineering from University of Hawaii. Before that, I got my master in physical oceanography from Ocean University of China in 1998. I joined CECO's NCTR and NOAA Center for Tsunami Research in 2006. So I just consider myself as a tsunami modeler. So the expertise is mostly in tsunami modeling and forecasting. So the scale of the tsunami problem is both global and local. And the key points relating to the scale include source magnitude, intensity, the historical impact, the energy transfer between the disturbance and the ambient water, as well as the warning system. Historically, more than 2,500 tsunamis has been documented since 2000 BC, and every major subduction zone on the Earth can generate tsunamis impacting coastline, either locally or globally. So the red stars represent more than 60 observable tsunami events since 2004. Within the two decades of time, the tsunami hazard has resulted in about like 250,000 deaths and about 280 billion US dollars damage in global scale. So at NCTR, in our group, we consider the tsunami hazards in two categories, short-term and long-term. So our short-term hazard assessment support NOAA's mission to issue real-time tsunami warning that includes flood forecast capability based on this deep ocean tsunami data assimilation. While a long-term assessment is referred as the application of modeling technology to identify potential impact. And our short-term and long-term hazard assessment models developed globally during the past 2 years is shown in the map below. As you can see, all the short-term assessment sites are along the U.S. coastlines and territories, where the NOAA tsunami warning system can provide inundation forecasting in real time during the event. The long-term locations, however, spread all over the world, focusing on assessing the potential tsunami hazard for those locations. So combining observations and modeling for tsunami warning and forecasts is a core mission of our group. So this integrated approach not only enhances like early warning capabilities, but also support risk mitigation strategies. So I'd like to take a moment to talk about it before moving to other related projects. It also gives the audience an idea about the current status of the tsunami warning and the forecast system at a large scale. So traditionally, the tsunami warning relied on seismic analysis, limited time, tide gauge observations, and also experience of the warning center staff. So this traditional method may sometimes result in false alarms. In the 1990s, PMEL, the Pacific Marine Environment Lab here, started to test prototypes of bottom pressure sensor in deep water for early tsunami detection. This technology matured in early 2000 and fostered the modern forecast system that integrates the observations and the model computation in real-time warning and the forecast. During the November 17, 2003 Rat Island event, the tsunami source was actually constrained for the first time using the measurements from the nearby bottom pressure sensors. The tsunami waves were successfully predicted by computer models about like 45 minutes before arrived in Hilo Harbor, Hawaii. This event was considered as a proof of concept event for the modern forecast methodology. So a year later, on the Boxing Day of 2004, the Indian Ocean tsunami occurred and generated by a magnitude 9.3 earthquake, which is about like 40% more energetic than the 1964 Alaska earthquake. This tragedy was due to the lack of early detection instruments or warning systems of any sort in the Indian Ocean. This awakening event served as a catalyst for developing modern tsunami forecasting systems in many countries, including US. So this slide shows the milestone of the evolution of the timeline for modern tsunami inundation forecast system in the US. By 2008, NOAA has already deployed an array of 39 tsunami buoy stations named DART around the Pacific, Western Atlantic, and also Caribbean. The DART buoys were designed and patented here at the lab at the PMEL. Up to date, it has been through like 4 generations from one direction to bi-directional signal transmitting, easy to deploy, and also the latest 4th generation featuring high frequency sampling rate that can separate the tsunami signals from the background seismic noise. Right now, the global DART array has grown to a total of 74 sensors providing real-time early detection and monitoring of tsunami waves. So the forecasting methodology developed by PMEL was fully tested and validated during the 2011 Japan event. This system, named SIFT, short-term inundation forecast of tsunamis, was put into full operation at both tsunami warning centers in 2013. So the tsunami forecast sequence built into SIFT emphasizes forecasting of flood impact induced by tsunamis, which is like about like steps further than the traditional offshore forecasting. SIFT forecasting starts with the tsunami source estimation using seismic information, DART data assimilation, and also pre-computed model database. The source can then be used for forwarding modeling to rapidly obtain the basin-wide or global scale forecast of tsunami propagation. This forecast is then used as boundary conditions to conduct like inundation modeling to predict tsunami impact for US harbors and coastlines at the risk. So there are right now about like 80 inundation forecast models integrated into the system across the Pacific, Atlantic, and also Caribbean. as indicated by the green dots in the figure. In Alaska, 17 models cover major harbors and coastal communities at high risk of tsunami hazards. So during the 2011 Japan tsunami, the inundation forecast model were launched based on a source constraint using the deep ocean dart buoy data. The inundation forecasts were then obtained about like 4 hours before tsunami arrived in Hawaii Islands. And this results showed a very good comparison with the observed waveform at the tide gauge. And also the system successfully predict the tsunami inundation at Kahului Harbor, which agreed well with the after event survey data. So since 2004, the SIFT tool has been used to like monitor, test, and validate almost every single tsunami event around the world. Where the colors here represent the maximum offshore wave amplitude, which is also indication of energy distribution, because the energy is like proportional to the square of the wave height. And Alaska remained, relatively quiet until 2018, when a series of large and shallow earthquakes with magnitude between 7.6 and 8.2 occurred in most of the eastern Aleutians and also Gulf of Alaska. So the enhancement in early detection is a key to improving forecast especially to the near field. The fourth generation DART features high frequency sampling rates that can separate tsunami signals from background seismic noises. So comparing to the old generations, the new generation DART can be placed much closer to the source region, which can improve early detection time to the order of like between 10 and 30 minutes. And the global navigation satellite system, GNSS, can detect the peak ground displacement from an earthquake just within a couple of minutes. So in recent years, NASA and NOAA, there's a collaborative research that allowed us to implement the GNSS-based rapid earthquake source algorithm named GFAST into the SIFT system. With sufficient GNSS detections, the GFAST can provide source magnitude estimates in about 90 to 120 seconds, and a source configuration in about 3 minutes of the earthquake. So other technologies that we are looking into include the smart cable equipped with sensors measuring pressure, acceleration, and temperature. The smart cables aim for direct in situ early detection of tsunamis for regions that are not covered by the sparse distribution of the tsunami buoys. In the meantime, we collaborate with colleagues at the NASA JPL to explore the ionospheric detection of earthquakes and tsunamis. The GNSS satellite can rapidly detect the atmospheric waves that produce ionospheric density difference incurred by earthquakes and tsunamis, which can then be inverted as the total electron content signatures to characterize the tsunami source for real-time forecast. So while earthquakes generate more than 80% of the tsunamis, the non-seismic origins such as landslides or volcanic eruptions can also generate tsunami, heavily impact coastlines, and also probably are more of acute problems in Alaska. The current warning systems do not have the capability to forecast non-seismic tsunamis. Enhancing the forecasting capability for non-seismic tsunamis using kind of innovative observational and modeling techniques is one of our primary research directions in the near future, actually. So in the Arctic, tsunami can be triggered by non-seismic events like landslides and the volcanic eruptions. The figures on the right shows the documented tsunami events in Alaska and Arctic, which show that nearly all tsunami events in the Arctic were triggered by landslides, and the landslides are likely the biggest source of tsunami threats in the Arctic. In the meantime, Alaska is home to over like 130, volcanoes and the volcanic fields that have been active within the last 2 million years. 90 of them have been active during the past like 10,000 years, and more than 50 of them have erupted since 1760. So volcanic eruption can display large volume of water and create powerful tsunami waves as well. So our group has not done extensive work on landslide-generated tsunamis in Alaska. Last August, a few of us were invited to join a panel on modeling perspectives at the Tsunami Hazards Guidance for Vessel Operators workshop in Valdez. This workshop was an inspiring gathering of experts, harbor masters, operators, and also community members. It is a great example of the kind of communication I think TSLAB will aim to foster in the future. Following that, we participated in a USGS-led modeling benchmarking workshop focusing on a field-scale sub-area landslide tsunami intercomparison study. International teams tested the models against the two Alaska's cases, Barry Arm, based on the mapped landslide volume, and also Tom Field, validated using observational data like tsunami run-up and tide gauge records back in, I think, during the event in 2015. The goal of this benchmarking workshop was to better understand the uncertainties across all the state-of-art landslide tsunami models. So in both test cases, we mainly modeled the tsunamis generated by sub-area landslides. Comparing to submarine landslides, modeling tsunami generated by sub-area landslides is more challenging as it requires accurate modeling of the air, water, land interactions, and often involves like multi-phase flow modeling. So our previous modeling efforts for landslide-generated tsunamis have primarily focused on submarine landslides as part of the site-specific tsunami hazard mapping project. Two recent examples shown here include the Fraser River Delta landslide in British Columbia, Canada, and also a historical landslide event in Suva, Fiji. In this Fiji case, we were able to validate our model results by comparing them with the observed inundation extents. So as many of you probably know that tsunami inundation mapping for local submarine landslide sources have been completed for several communities in Alaska. Here, I'd like to acknowledge the important contributions from our colleagues at the Alaska Earthquake Center, particularly Elena Solomali and also Dmitry Nikolsky in leading these efforts. But a significant work remains for many other coastal communities, largely due to a limited information on potential landslide sources, especially sub-area landslides. Addressing these gaps is, I think, a key objective of the TSLAB community. So for tsunamis generated by volcanic eruptions, it has become increasingly clear in recent years that the data from atmospheric and weather observations, when combined with real-time coastal and deep water tsunami detection, can provide the necessary input for model forecasts before a non-seismic tsunami impacts the coastline. Our proof of concept forecast methodology effectively combines the measurements of the air pressure waves with real-time tsunami observation to provide model predictions. And this approach proved to be valid during the Tonga volcanic tsunami that occurred on January 15, 2022. The video on the right shows both the propagation of the air pressure wave and also the tsunami wave generated by the volcanic eruptions, like wrapping around the globe. The Tonga eruption generated tsunami waves that reached across the globe with amplitudes exceeding like 1 meter even in the far field. These waves were detected in real time by the tsunami buoy network, especially in the Pacific. Simultaneously, atmospheric pressure signals were recorded by weather stations and also instruments worldwide. We now understand that the global propagation of these tsunami waves were primarily driven by the atmospheric pressure waves known as like Lam wave. The model prediction on the right using the Lam wave agreed well with the deep ocean buoy observations. So the source mechanisms of volcanic tsunamis are kind of complex, and several key types are listed here. For the Tonga event, we likely can rule out the volcanic earthquakes as a primary source, but the slope instability and the pyroclastic flows likely occur during the eruption. Some studies suggest that the small amplitude early waves observed before the main eruption probably were linked to those processes. In this study, our focus here is like on the main eruption, which includes the atmospheric Lam wave, which I showed in last slide, and also the eruption triggered initial shock wave, as well as the resulting caldera collapse. So the shock wave and also the caldera collapse are responsible for the impact in the near field, where the tsunami height reaches like up to 20 meters, and also maximum inundation extending about like 1 kilometer inland on Tongatapu Island. So the wavelet analysis here show that the model results considering the shock wave, the Lam waves, and also the caldera collapse can provide reasonable comparison with the measurements in terms of the spectrum energy, the wave period, and also the temporal evolution of waves. The modeled short wave aligned particularly well with the measurements across all three instruments, which include a dart buoy and also 2 tide gauges in the near field. It is important to acknowledge that the uncertainties about the eruption, particularly in terms of their energy release and timing, remain substantial. They also represent significant challenge in volcanic tsunami forecasting. So in the next few slides, I'd like to discuss some of our ongoing projects that, in my opinion, may potentially align with TSLIP proposals, although they don't directly address the landslide hazards, but I hope they can serve as a source of like sparkling ideas that can complement the broader objectives of the TSLIP. So this is a project. This project is a collaborative effort involving researchers from UW, NOAA, and also USGS. It is mainly supported by the NSF Cascade Coastal and People COPES Research Hub. And the goal of this project is to improve the estimation of hazards from megastruts, earthquakes, and tsunamis in the Cascadia subduction zone using coupled 3D earthquakes and tsunami simulations. So to achieve these, we first use high-performance computing to conduct 3D modeling for a wide range of possible earthquakes events in the Cascadia subduction zone. So from these simulations, we generate comprehensive data sets on ground shaking and create intensity maps that can show the distribution spatial distribution, also intensity of the earthquake shaking across the Pacific Northwest region. And then the ground motion data from the 3D earthquake modeling can then be used to analyze the cascading effects of earthquakes, like the damages to the infrastructures, generation of tsunamis, and also vertical land movement. In particular, the ground shaking data can be used to assess slope instabilities and triggering of potential landslides. So this approach allowed us to assess the full spectrum of earthquake hazards and their potential consequences on communities and environment. So this work leverages USGS full margin 3D kinematic or seismic modeling that utilizes a high resolution velocity model to accurately capture the Earth's structure, the directivity effects, the basin amplification, and other critical factors that influence the propagation of seismic waves, as shown by the animation at bottom. So a suite of distinct earthquake scenarios is then generated by varying the key earthquake parameters. So this is accomplished by a logic tree approach, which can systematically explore the range of possible megathrust events in the Cascadia subduction zone. So using the earthquake motion data, we couple the vertical ground motion into tsunami models to simulate the regional impact of tsunami waves corresponding to kinematic rupturing process. So the videos on the right demonstrate the coast-seismic vertical displacement caused by the earthquake motion. Simultaneously, the earthquake triggers tsunami, and the tsunami waves propagate as the earthquake, the kinematic rupturing process unfolds. When we track the progression of the maximum tsunami height over time, you can clearly see the focusing of tsunami energy along the coastline. That's predominantly guided by the ocean bathymetry. And the second project that is the tsunami-induced currents, which can pose serious hazards both inside and outside ports, often lasting for hours after initial wave arrival. The strong, rapidly shifting currents can damage vessels, port infrastructures, and the mooring systems, even when the wave heights are relatively small. The hazardous high-speed currents, they usually occur in and around the harbors, especially around the harbor structures, where the flow, acceleration, and the separation are dramatic. And also the dramatic whirlpool phenomenon that you probably have seen this during the 2011 Japan tsunami. So these whirlpools resulted from complex interaction between incoming and reflected tsunami waves, and also geometry of the coastal and harbor features. And such events, they just underscore the importance of modeling not only the wave heights, but also currents and also flow patterns to accurately assess the tsunami risks. So mapping of these maritime hazards provide critical information for harbor authorities and also vessel operators. Here is a project. It's ongoing research that focuses on combined impact of the onshore inundation and morphodynamic changes of, including sediment transport, which is a new aspect of the inundation hazards that has not been considered in any of the existing tsunami inundation maps yet. So in this example, we use a high resolution model to investigate tsunami-induced morphodynamic changes and its impact on inundation hazards at Seaside, Oregon. On the left are videos showing the simulated erosion in warm color and the deposition in cold color of the sediments. So the figures on the right can indicate that the tsunami inundation actually increases when sediment transport is integrated in the tsunami inundation. In this case, the first and also the largest wave levels the sand dunes along the beachfront and allows the following waves to penetrate farther inland. And tsunami-induced debris is a critical and often overlooked aspect of coastal vulnerability. The 2011 Japan video footage shows once it reaches the coast regions, the tsunami can basically features flow of debris that can cause human loss, damage to infrastructures, severe disruption of the critical lifeline, and also environmental consequences. And also the National Tsunami Hazard Mitigation Program recognized the need for improved tsunami debris modeling as a future research challenge. So our pilot study on tsunami inundation and the debris modeling informed this award-winning design of Oregon State University Hatfield Marine Science Center in Newport, Oregon, which also functioned as a tsunami evacuation shelter for up to 2,000 people for the local community. So from this image, you can see this like 48-foot high building finished with a ramp leading to the rooftop. So on the right is a video showing the model predicted movement of tsunami debris from a magnitude 9.1 cascaded subduction zone event. The architects and the engineers, they were concerned if the nearby, like there's NOAA ships, OSU research vessels, and also cargo ships inside the bay, would they impact on the building or not? As a result, an anti-crust zone with filled gravels was incorporated on the rooftop to mitigate the impact force from large vessels during a tsunami. So prediction of tsunami debris hazards still remain very challenging due to uncertainties and also the lack of field data for validation. So as we continue to adapt to the new technology, AI, of course, now stands out as a transformative force impacting our daily lives. So we developed a prototype AI model to assist in tsunami forecasting. So this AI model generates tsunami source determination and waveform forecast using incomplete data, and show in the example using a waveform up to like 60 minutes at the entrance of a strait of Juan de Fuca. The AI model can perfectly predict the waveforms up to 5 hours, reaching inside the Puget Sound. So with sufficient training data, I would think maybe an AI model can be properly trained to quickly predict tsunami hazards in distant harbors and the communities like, say, Whittier, from rapid like measurements of landslide motion and water levels near Barry Arm. So this could be something that we can explore in the future. So I got a question now about all the research needs and everything. So I list here is a list I come up with for research needs and opportunities towards the future TSLAB proposals. So like the advanced modeling for landslide dynamics and the tsunami generation, particularly for sub-area landslides. And maybe we'll also think about advanced modeling of 3D earthquake ground motion, so that can be used to see if they trigger landslide, instability and trigger landslides or not. And also, there's like emergency planning and mapping for maritime hazards. Implementing practical landslide forecasting technology in the next generation forecast system that combines observations and models, which is part, maybe AI can be part of it. Also, the probabilistic landslide tsunami risk assessment can be a future topic. And also engineering and the infrastructure risk. The slide could include impact of landslide tsunamis on infrastructures, design of resilient coastal infrastructures in a high-risk area, and also risk mitigation strategy for ports, pipelines, also sediments. So, of course, there's constraints and the challenges like reconnaissance studies and monitoring of high-risk landslide slopes, high-quality DMs due to changing environment and the geophysical conditions. And also from the USGS modeling benchmarking workshop, we can see that there's still a lot of modeling uncertainties, among all different models. And also sparse historical data. Maybe that's one of the reasons why the modern modeling uncertainties are so big. And right now, the probability of landslides are not well established. Of course, sustained funding in the future, to support all these research activities. Yep, here I'm going to wrap up my talk. So I'd like to, open the ground for questions and discussions. Thank you.
All right, thank you so much. I see a hand up already, but I am just going to pause the recording quick before we move on to our question and answer session.